In a previous video, we've gone through two possible ways of proving that two shapes are similar. The first way was if we can show that a shape is dilated using a center of dilation and a scale factor, then the shapes are similar, and we went through how to do that. Step 2, or method number 2, if corresponding sides are proportional and corresponding angles are congruent, then we know the two shapes are similar. And then the last method is number 3. If you can use transformations to map one shape onto the other, then the shapes are similar. If you can take your pre-image and through rotation, reflection, dilation, and translation, you can get from the pre-image to the final image, then you know that those two shapes are similar. Let's take a look at an example of that. So if you take a look at our graph here, we've got a pre-image. Here's our starting point. Can we use transformations to get from here to here? If we can do that, then we have proved that those two shapes are similar. Now, I'm going to teach you guys something. When you are going through this method of proving similarity, I would say that you do the 4 transformations in this order. Rotate first, reflect next, dilate next, translate next. There is your proper order. If you do it that way, it usually is a little bit easier to accomplish your goal. So start with rotation first, then check and see if there is reflection, then see if there is dilation, then see if there is translation. That is the order that you should go in to accomplish this particular thing. So let's go ahead and follow that. First thing is, starting from our pre-image, does it appear there's a rotation? Does it look like we rotated the pre-image around to get to our image? And the answer is no. If you rotate this, if you cut out this triangle and you rotate it around to here, you'd see that the hypotenuse would be on the bottom. So there's no rotation. So we're going to skip that one. How about reflection? Well, it looks to me like to get from here to here, we're going to have to either reflect it across the y-axis or reflect it across the x-axis. And I can see this appears to be a reflection across the y-axis. So I'm going to say there's a reflection, yes, and that's going to be across the y-axis. Let's do that now. So when I reflect across the y-axis, I'm going to show you this down below in the notes. There's our transformation notation for reflecting across the y-axis. xy becomes negative xy. So let's go ahead and reflect that. When I perform that transformation, I'm going to get this point, and let's see, 1, 2, 3, 4, 1, 2, 3, 4. So I used the y-axis as a mirror, and I just counted the same number of units to the left that there are to the right. And that gave me my reflected shape. I'm not going to go through every single coordinate. You can do that if you need to. In fact, with rotation, you might have to so you don't mess it up. But there is our first new triangle. We have done a reflection. And I'm going to actually call that transformation number 1. Let's call this 1. There's our first transformation. Okay, how about dilation? Well, now that we're here, it does look like we have to make the triangle bigger. Let's find out how much bigger. Let's pick a corresponding side. The height of this triangle is 2. The height of our final triangle is 4. Well, that looks like a scale factor of 2. So we're going to say, are we going to dilate? Yes. And in this case, let's go ahead and do our transformation notation so that we end up getting the right points. So we're going to say the scale factor here is going to be equal to 2 to 1. We already checked that on our sides. And that we know, class, is going to be an enlargement, which is what we want. Remember, 2 to 1 means 2 over 1. That value is 2. 2 over 1 is equal to 2. A scale factor greater than 1 is an enlargement. Less than 1 is a reduction. So we're going to enlarge this. But let's do our transformation notation, or we're going to mess this up. So That means we're going to take our point A, and let's go ahead and label that here. I'm going to label this as just real small print. Let's put A here, and let's call this B, and let's call this C. So A is currently at -1, 1. Our new value for A is going to be A prime, and that's going to be at, remember, we're going to multiply all of our values. When you do a dilation by a scale factor of 2, you're going to multiply the numbers. So -1 times 2 is -2. 1 times 2 is 2. There's our new A value. Our B value is currently, looks like it's -1, 3. We're going to multiply all those coordinates, those two coordinates, by 2. That gives us -2, 6. And then our C coordinate appears to be at -4, 1. That means our new C value is going to be at -8, 2. So there's our new point. Let's go ahead and plot them. I'll pick a different color here so we can see it a little bit better. So let's say A is at -2, 1, 2, and +2, 1, 2. It actually ends up being right here. And our B value is going to be -2, 6, 2, 3, 4, 5, 6. And our C value is -1, 2, 3, 4, 5, 6, 7, 8, 1, 2 right here. Alright, let's connect those. So now we've just done a dilation by a scale factor of 2, because we know that our final triangle was 2 times as big as our original. We compared the corresponding sides together. Alright, that's looking pretty good. And let's make a note here. That was our second transformation. Let's label that as triangle 2. Alright, so now that we've dilated, we got one more thing to do, and that's translate. All we need to do now is slide this triangle 2 down to our final location. So is there a translation here? Absolutely. We're going to have to slide this to its final resting place. Now the question is, how far are we sliding it? Well, we're going to go right 1. We've got to move over 1 to get it to line straight up and down. So it's going to be right 1, and then we're going to go down. Let's check it. We go right 1, 1, 2, 3, 4, 5, 6. Notice I picked a point and just slid it over right and then down 6. And that's going to get our final triangle where it is supposed to be. And then our final location is going to be due to transformation 3. And there is our final triangle at position number 3. And now once you've done that, as we're working on that class, really the end goal is not just to show the transformations on the grid, but also to write down what we did. So here's what we did to transform the pre-image to the image. We reflected across the y-axis. There was our transformation notation. We dilated by a scale factor of 2. And then we translated right 1 and down 6. So this paragraph describes exactly what we did step by step to get from the pre-image to the final image, which was down here below. Alright, let's do another one. This will be a little more complicated. So, well, back to this again. So here's our issue is, can you map the pre-image onto the image using the 4 transformations? If you can do that, you have proved similarity. If it's not possible, or if you try to do that and you end up with a triangle that doesn't look the same as the final copy or the final image, then you know they are not similar. Alright, using transformations, prove that the 2 shapes on the grid are similar. Now I can tell you right now, it's pretty simple to figure out whether they are similar or not. In fact, I can tell you these 2 triangles are congruent. If they're congruent, they must be similar. Because all similar shapes, all congruent shapes are also similar. They just have a scale factor of 1. So, here's our pre-image. Let's take a look and see, do we have to do rotation? Man, if I look at this right now, I can see that this triangle is going to have to get rotated. If if you see this, you're going to have to rotate this clockwise. We're going to turn this so that the pointier side is facing down. So I know there's rotation here. Always check rotation first. And we are definitely rotating 90 degrees, and that's going to be clockwise. Same direction as the hands of a clock. 90 degrees clockwise. Now, again, when you rotate, you're going to want to use transformation notation so you don't guess at the wrong point. And I'll give you these hints as you work through these. We're going to rotate 90 degrees. That means our transformation notation is xy becomes y negative x. So let's take a look at our current points on our preimage. Let's call this A, and we'll call this B, and we'll call this C. Looks like our A value, the coordinates are at negative 5, 3. Our B coordinates are at negative 2, 3, and our C coordinates are at negative 5 and 1. We've got to get these to be our new coordinates. So I'm going to find what A prime is, what B prime is, and what C prime is. Let's take a look at our transformation notation. xy becomes y negative x. Let's put a little note here so we see this, okay? So xy is going to become y negative x. So here is our y value at 3. 3 is going to move to the front of our coordinate, so that's 3. And our x value is going to go to the back of our coordinate and flip sign. That's positive 5. Let's take a look at B. Our y value for B was 3, so that's going to move to the front of our B prime, so that's also 3. The x value is going to move to the back. Remember, when you do a rotation, sometimes the x and the y value flip places. They do that here. So B was negative 2. For the x value, that's going to move to the end of the new coordinate and flip the sign. And then for C, the y value moves to the front, this x value moves to the back and flips sign. Let's go ahead and plot those points now. So I've got 3, 5, 1, 2, 3, 1, 2, 3, 4, 5. There's our A. Okay, and then actually, sorry, 1, 2, 3, 1, 2, 3, 4, 5. There's our A value. Then B is 1, 2, 3, 1, 2. And our C value is 1, 1, 2, 3, 4, 5. So, as weird as this looks, this is the new location for our triangle ABC rotated 90 degrees clockwise. And we're going to call that transformation number 1. So there's our triangle with transformation number 1, rotation. Okay, let's take a look. After we get to there, is there a reflection? It certainly does not look like it. The orientation is exactly the same now. So reflect? No. How about dilate? Well, it appears these two shapes are the same size. This leg is 2, this leg is 2, this leg is 3, this leg is 3. There's no dilation. And for translate, yes there is. We have to get from our current location to our new location. Let's take a look at what we're doing here. I'll pick the corner here, the 90 degrees. We're going to move 2 to the right and 1, 2, 3, 4, 5, 6 down. So right 2 and down 6. And that's going to get us, that's our transformation number 2, and that's going to get us to triangle number 2, which is our final spot that we want to get to. Alright, so we can see by rotating 90 degrees clockwise and translating 2 right and 6 down, we're going to end up in our final spot. That means we know these two triangles are similar. So we have proved so they are similar. And let's just put a little note here. Hey, we found it's kind of weird. The scale factor is actually 1 to 1. is 1 to 1, which actually gives us a congruent shape. But it still counts as similar because congruent shapes are still considered similar with a scale factor of 1 to 1. And then if you want to describe your transformations, here they are. We had to rotate 9 degrees clockwise. There was our transformation notation. And then we had to translate right 2 and down 2. And here is our transformation notation for that. X becomes x plus 2, y becomes y minus 6. So here is our third and final way of using transformations to prove whether two shapes are similar or not. This takes some practice. I'll get you some worksheets in class with some practice so you can get some ideas as to how to accomplish this.